In the next few videos, I'd like to talk about machine learning system design. These videos will touch on the main issues that you may face when designing a complex machine learning system, and I'd like to try to give advice on how to strategize putting together a complex machine learning system. In case this next set of videos seems a little disjointed, that's because these videos will touch on a range of the different issues that you may come across when designing complex learning systems. And even though the next set of videos may seem somewhat less mathematical, I think that this material may turn out to be very useful and potentially huge time savers when you're building big machine learning systems. Concretely, I'd like to begin with the issue of prioritizing how to spend your time on what to work on, and I'll begin with an example on spam classification. Let's say you want to build a spam classifier. Here are a couple of examples of obvious spam and non-spam email, with the one on the left trying to sell things. And notice how spammers will sometimes deliberately misspell words like medicine with a 1 there, and mortgages. And on the right is a maybe obvious example of non-spam email, actually email from my younger brother. Let's say we have a labeled training set of some number of spam emails and some non-spam emails, denoted with labels y equals 1 or 0. How do we build a classifier using supervised learning to distinguish between spam and non-spam? In order to apply supervised learning, the first decision we must make is how do we want to represent X, that is the features of the email. Given the features X and the labels Y in our training set, we can then train a classifier, for example, using logistic regression. Here's one way to choose a set of features for our emails. We could come up with, say, a list of maybe 100 words that we think are indicative of whether email is spam or non-spam. For example, if a piece of email contains the word deal, maybe it's more likely to be spam. If it contains the word buy, maybe more likely to be spam. A word like discount, more likely to be spam. Whereas if a piece of email contains my name, Andrew, maybe that means the person actually knows who I am, and that might mean it's less likely to be spam. And maybe for some reason I think the word now may be indicative of non-spam because I get a lot of urgent emails, and so on, and maybe we choose 100 words or so. Given a piece of email, we can then take this piece of email and encode it into a feature vector as follows. I'm going to take my list of 100 words and sort them in alphabetical order, say. Doesn't have to be sorted, but here's my list of words, this count, and so on, and eventually I'll get down to now, and so on. And given a piece of email like that shown on the right, I'm going to check and see whether or not each of these words appears in the email, and then I'm going to define a feature vector X, where in this piece of email on the right, my name doesn't appear, so I'm going to put a 0 there. The word buy does appear, so I'm going to put a 1 there, and I'm just going to put ones or zeros. I'm going to put a 1 even though the word buy occurs twice. I'm not going to really count how many times the word occurs. The word deal appears, I'm going to put a 1 there. The word discount doesn't appear, at least not in this little short email, and so on. The word now does appear, and so on. So I put ones and zeros in this feature vector depending on whether or not a particular word appears. And in this example, my feature vector would have dimension 100 if I have a 100, if I chose 100 words to use for this representation. And each of my features xj will basically be 1 if a particular word, let me call this word j, appears in the email, and xj would be 0 otherwise. Okay, so that gives me a representation, a feature representation of a piece of email. By the way, even though I described this process as manually picking 100 words, in practice what's most commonly done is to look through a training set, and in the training set to pick the most frequently occurring n words, where n is usually between 10,000 and 50,000, and use those as your features. So rather than manually picking 100 words, you look through the training examples and pick the most frequently occurring words, like 10,000 to 50,000 words, and those form the features that you're going to use to represent your email for spam classification. Now, if you're building a spam classifier, one question that you may face is, what's the best use of your time in order to make your spam classifier have high accuracy or have low error? One natural inclination is to go and collect lots of data, right? And in fact, there's this tendency to think that, well, the more data we have, the better the algorithm will do. And in fact, in the email spam domain, there are actually pretty serious projects called honeypot projects, which create fake email addresses and try to get these fake email addresses into the hands of spammers and use that to try to collect tons of spam email and therefore get a lot of spam data to train learning algorithms on. But we've already seen in the previous sets of videos that getting lots of data will often help, but not all the time. But for most machine learning problems, there are a lot of other things you could usually imagine doing to improve performance. For spam, one thing you might think of is to develop more sophisticated features on the email, maybe based on the email routing information. And this would be information contained in the email header. So when spammers send email, very often they will try to obscure the origins of the email and maybe use fake email headers or send the email through very unusual sets of compute servers, through very unusual routes in order to get the spam to you. And some of this information will be reflected in the email header. And so one can imagine looking at the email headers and trying to develop more sophisticated features to capture the sort of email routing information to identify if something is spam. Something else you might consider doing is to look at the email message body, that is the email text, and try to develop more sophisticated features. For example, should the word discount and the word discounts be treated as the same word? Or should we have treat the words deal and dealer as the same word, maybe even though one is lowercase and one is capitalized in this example? Or do we want more complex features about punctuation, because maybe spammers use exclamation marks a lot more, I don't know. And along the same lines, maybe we also want to develop more sophisticated algorithms to detect and maybe to correct deliberate misspellings like the mortgage, medicine, watches. Because spammers actually do this because if you have watches with a 4 in there, then, well, with the simple technique that we talked about just now, the spam classifier might not equate this as the same thing as the word watches, and so it may have a harder time realizing that something is spam with these deliberate misspellings, and this is why spammers do it. When working on a machine learning problem, very often you can brainstorm lists of different things to try like these. And by the way, I've actually worked on the spam problem myself for a while, and actually spent quite some time on it. And even though I kind of understand the spam problem, I actually know a bit about it, I would actually have a very hard time telling you of these 4 options, which is the best use of your time. So what happens, frankly, what happens far too often is that a research group or a product group will randomly fixate on one of these options. And sometimes that turns out not to be the most fruitful way to spend your time, depending on which of these options someone ends up randomly fixating on. By the way, in fact, if you even get to the stage where you brainstorm a list of different options to try, you're probably already ahead of the curve. Sadly, what most people do is, instead of trying to list out the options of things you might try, what far too many people do is wake up one morning and for some reason just have a weird gut feeling that, oh, let's have a huge honeypot project to go and collect tons more data. And for whatever strange reason, just sort of wake up one morning and randomly fixate on one thing and just work on that for 6 months. But I think we can do better. And in particular, what I'd like to do in the next video is tell you about the concept of error analysis and talk about a way where you can try to have a more systematic way to choose amongst the options of the many different things you may work on, and therefore be more likely to select what is actually a good way to spend your time, for the next few weeks or next few days or the next few months. In the last video, I talked about how when faced with a machine learning problem, there are often lots of different ideas for how to improve the algorithm. In this video, I'd like to talk about the concept of error analysis, which will hopefully give you a way to more systematically make some of these decisions. If you're starting work on a machine learning problem or building a machine learning application, it's often considered very good practice to start not by building a very complicated system with lots of complex features and so on, but to instead start by building a very simple algorithm that you can implement quickly. And when I start with a learning problem, what I usually do is spend at most one day, like literally at most 24 hours, to try to get something really quick and dirty, frankly not at all sophisticated system, but get something really quick and dirty running and implement it and then test it on my cross-validation data. Once you've done that, you can then plot learning curves. This was what we talked about in the previous set of videos, but plot learning curves of the training and test errors to try to figure out if your learning algorithm may be suffering from high bias or high variance or something else, and use that to try to decide if having more data, more features, and so on are likely to help. And the reason that this is a good approach is often when you're just starting out on a learning problem, there's really no way to tell in advance whether you need more complex features or whether you need more data or something else, and it's just very hard to tell in advance. That is, in the absence of evidence, in the absence of seeing a learning curve, it's just incredibly difficult to figure out where you should be spending your time. And it's often by implementing even a very, very quick and dirty implementation and by plotting learning curves that helps you make these decisions. So if you like, you can think of this as a way of avoiding what's sometimes called premature optimization in computer programming. And this is an idea that just says that we should let evidence guide our decisions on where to spend our time rather than use gut feeling, which is often wrong. In addition to plotting learning curves, one other thing that's often very useful to do is what's called error analysis. And what I mean by that is that when building, say, a spam classifier, I will often look at my cross-validation set and manually look at the emails that my algorithm is making errors on. So look at the spam emails and non-spam emails that the algorithm is misclassifying, and see if you can spot any systematic patterns in what type of examples it is misclassifying. And often by doing that, this is the process that will inspire you to design new features, or they'll tell you what are the current things or current shortcomings of the system and give you the inspiration you need to come up with improvements to it. Concretely, here's a specific example. Let's say you've built a spam classifier and you have 500 examples in your cross-validation set, and let's say in this example that the algorithm has a very high error rate and it misclassifies 100 of these cross-validation examples. So what I do is manually examine these 100 errors and manually categorize them based on things like what type of email it is and what cues or what features you think might have helped the algorithm classify them correctly. So specifically by what type of email it is, if I look through these 100 errors, I might find that maybe the most common types of spam emails it misclassifies are maybe emails on pharma or on pharmacies, basically emails trying to sell drugs, maybe emails that are trying to sell replicas, so sort of fake watches, fake random things, maybe have some emails trying to steal passwords. These are also called phishing emails, but that's another big category of emails, and maybe other categories. So in terms of classify what type of email it is, I would actually go through and count up, of my 100 emails, maybe I find that 12 of them mislabeled emails are pharma emails, and maybe 4 of them are emails trying to sell replicas, like sell fake watches or something. And maybe I find that 53 of them are these what's called phishing emails, basically emails trying to persuade you to give them your password, and 31 emails are other types of emails. And it's by counting up the number of emails in these different categories that you might discover, for example, that the algorithm is doing really particularly poorly on emails trying to steal passwords, and that might suggest that it might be worth your effort to look more carefully at that type of email and see if you can come up with better features to categorize them correctly. And also what I might do is look at what cues or what features, additional features might have helped the algorithm classify the emails. So let's say that some of our hypotheses about things or features that might help us classify emails better are trying to detect deliberate misspellings versus unusual email routing versus unusual, spammy punctuation, such as if people use a lot of exclamation marks. And once again, I would manually go through and let's say I find 5 cases of this and 16 of this and 32 of this and a bunch of other types of emails as well. And if this is what you get on your cross-validation set, then it really tells you that maybe deliberate spellings is a sufficiently rare phenomenon that maybe is not worth a lot of time trying to write algorithms to detect that. But if you find a lot of spammers are using, unusual punctuation, then maybe that's a strong sign that it might actually be worth your while to spend the time to develop more sophisticated features based on the punctuation. So this sort of error analysis, which is really the process of manually examining the mistakes that the algorithm makes, can often help guide you to the most fruitful avenues to pursue. And this also explains why I often recommend implementing a quick and dirty implementation of an algorithm. What we really want to do is figure out what are the most difficult examples for an algorithm to classify. And very often, for different algorithms, for different learning algorithms, they'll often find similar categories of examples difficult. And by having a quick and dirty implementation, that's often a quick way to let you identify some errors and quickly identify what are the hard examples so that you can focus your efforts on those. Lastly, when developing learning algorithms, one other useful tip is to make sure that you have a numerical evaluation of your learning algorithm. And what I mean by that is that if you're developing a learning algorithm, it's often incredibly helpful if you have a way of evaluating your learning algorithm that just gives you back a single row number, maybe accuracy, maybe error, but a single row number that tells you how well your learning algorithm is doing. I'll talk more about this specific concept in later videos, but here's a specific example. Let's say we're trying to decide whether or not we should treat words like discount, discounts, discounted, discounting as the same word. So, maybe one way to do that is to just look at the first few characters in a word. Like, if you just look at the first few characters of a word, then you figure out that maybe all of these words have similar meanings. In natural language processing, the way that this is done is actually using a type of software called stemming software. If you ever want to do this yourself, search on a web search engine for the Porter stemmer, and that would be one reasonable piece of software for doing this sort of stemming, which will let you treat all of these words, discount, discounts, and so on, as the same word. But using a stemming software that basically looks at the first few alphabets of a word, more or less, it can help but it can hurt. And it can hurt because, for example, the software may mistake the words universe and university as being the same thing because these two words start off with very similar with the same alphabets. So if you're trying to decide whether or not to use stemming software for a spam classifier, it's not always easy to tell, and in particular, error analysis may not actually be helpful for deciding if this sort of stemming idea is a good idea. Instead, the best way to figure out if using stemming software is going to help your classifier is if you have a way to very quickly just try it and see if it works. And in order to do this, having a way to numerically evaluate your algorithm is going to be very helpful. Concretely, maybe the most natural thing to do is to look at the cross-validation error of the algorithm's performance with and without stemming. So if you run your algorithm without stemming and you end up with, let's say, 5% classification error, and you rerun it and you end up with, let's say, 3% classification error, then this decrease in error very quickly allows you to decide that, looks like using stemming is a good idea. For this particular problem, there's a very natural single row number evaluation metric, namely the cross-validation error. We'll see later examples where coming up with this sort of single row number evaluation metric may need a little bit more work. But as we'll see in a later video, doing so will also then let you make these decisions much more quickly of, say, whether or not to use stemming. And just as one more quick example, let's say that you're also trying to decide whether or not to distinguish between upper versus lowercase. So, is the word mom with uppercase m versus lowercase m, I mean, should that be treated as the same word or as different words? Should these be treated as the same feature or as different features? And so once again, because we have a way to evaluate our algorithm, if you try this out, if I stop distinguishing upper and lowercase, maybe I end up with 3.2% error, and I find that therefore this does worse than if I use only stemming, and so this lets me very quickly decide to go ahead and to distinguish or to not distinguish between upper and lowercase. So when you're developing a learning algorithm, very often you'll be trying out lots of new ideas and lots of new versions of your learning algorithm. If every time you try out a new idea, if you end up manually examining a bunch of examples again to see if it got better or worse, that's going to make it really hard to make decisions on do you use stemming or not, do you distinguish upper and lowercase or not. But by having a single row number evaluation metric, you can then just look and see, did the error go up or go down? And you can use that to much more rapidly try out new ideas and almost right away tell if your new idea has improved or worsened the performance of the learning algorithm. And this will let you often make much faster progress. So the strongly recommended way to do error analysis is on the cross-validation set rather than the test set, but there are people that will do this on the test set, even though that's definitely a less mathematically appropriate, so the less recommended thing to do than to do error analysis on your cross-validation set. So to wrap up this video, when starting on a new machine learning problem, what I almost always recommend is to implement a quick and dirty implementation of your learning algorithm. And I've almost never seen anyone spend too little time on this quick and dirty implementation. I've pretty much only ever seen people spend much too much time building their first, supposedly quick and dirty implementation. So really, don't worry about it being too quick, or don't worry about it being too dirty, but really implement something as quickly as you can. And once you have the initial implementation, this is then a powerful tool for deciding where to spend your time next, because first you can look at the errors it makes and do this sort of error analysis to see what mistakes it makes and use that to inspire further development. And second, assuming your quick and dirty implementation incorporated a single row number evaluation metric, this can then be a vehicle for you to try out different ideas and quickly see if the different ideas you're trying out are improving the performance of your algorithm, and therefore let you maybe much more quickly make decisions about what things to fold in or what things to incorporate into your learning. In the previous video, I talked about error analysis and the importance of having error metrics, that is, of having a single row number evaluation metric for your learning algorithm to tell how well it's doing. In the context of evaluation and of error metrics, there's one important case where it's particularly tricky to come up with an appropriate error metric or evaluation metric for your learning algorithm. That case is the case of what's called skewed classes. Let me tell you what that means. Consider the problem of cancer classification, where we have features of medical patients and we want to decide whether or not they have cancer. So this is like the malignant versus benign tumor classification example that we had earlier. So let's say y equals 1 if the patient has cancer and y equals 0 if they do not. We might train a logistic regression classifier, and let's say we test our classifier on a test set and find that we get 1% error. So we're making 99% correct diagnoses. Seems like a really impressive result, right? We're correct 99% of the time. But now, let's say we find out that only 0.5% of patients in our training and test sets actually have cancer. So only 0.5% of the patients that come through our screening process have cancer. In this case, the 1% error no longer looks so impressive. And in particular, here's a piece of code, here's actually a piece of non-learning code that takes this input to features x and it ignores it. It just sets y equals 0 and it always predicts, nobody has cancer. And this algorithm would actually get 0.5% error. So this is even better than the 1% error that we're getting just now. And this is a non-learning algorithm that's, it's just predicting y equals 0 all the time. So the setting of when the ratio of positive to negative examples is very close to one of the two extremes, where in this case the number of positive examples is much smaller than the number of negative examples because y equals 1 so rarely. This is what we call the case of skewed clauses, where we just have a lot more of examples from one clause than from the other clause. And by just predicting y equals 0 all the time, or maybe by predicting y equals 1 all the time, an algorithm can do pretty well. So the problem with using classification error or classification accuracy as our evaluation metric is the following. Let's say you have one learning algorithm that's getting 99.2% accuracy. So that's a 0.8% error. Let's say you make a change to your algorithm and you now are getting 99.5% accuracy. That is 0.5% error. So is this an improvement to the algorithm or not? One of the nice things about having a single row number evaluation metric is this helps us to quickly decide if we just made a good change to the algorithm or not. By going from 99.2% accuracy to 99.5% accuracy, did we just do something useful, or did we just replace our code with something that just predicts y equals 0 more often? So if you have very skewed clauses, it becomes much harder to use just classification accuracy because you can get very high classification accuracies or very low errors, and it's not always clear if doing so is really improving the quality of your classifier, because predicting y equals 0 all the time doesn't seem like a particularly good classifier. But just predicting y equals 0 more often can bring your error down to maybe as low as 0.5%. When we're faced with such skewed clauses, therefore, we would want to come up with a different error metric or a different evaluation metric. One such evaluation metric are what's called precision recall. Let me explain what that is. Let's say we're evaluating a classifier on a test set. For the examples in the test set, the actual class of that example in the test set is going to be either 1 or 0, right? If there's a binary classification problem. And what our learning algorithm will do is it will predict some value for the class, and our learning algorithm will predict a value for each example in my test set, and the predicted value will also be either 1 or 0. So let me draw a 2x2 table as follows, and I'll fill in these entries depending on what was the actual class and what was the predicted class. If we have an example where the actual class is 1 and the predicted class is 1, then that's called an example that's a true positive, meaning our algorithm predicted that it's positive, and in reality the example is positive. If our learning algorithm predicted that something is negative, class 0, and the actual class is also class 0, then that's what's called a true negative. We predicted 0 and it actually is 0. To fill in the other two boxes, if our learning algorithm predicts that a class is 1, but if the actual class is 0, then that's called a false positive. So that means our algorithm thought the patient has cancer, but in reality the patient does not. And finally, the last box is a 0, 1. That's called a false negative, because our algorithm predicted 0, but the actual class was 1. And so we have this little sort of 2x2 table based on what was the actual class and what was the predicted class. So here's a different way of evaluating the performance of our algorithm. We're going to compute two numbers. The first is called precision. And what that says is, of all the patients where we predicted that they have cancer, what fraction of them actually have cancer? So let me write this down. The precision of a classifier is the number of true positives divided by the number that we predicted as positive. Right? So of all the patients that, we went to those patients and we told them we think you have cancer. Of all those patients, what fraction of them actually have cancer? So that's called precision. And another way to write this would be true positives, and then in the denominator is the number of predicted positives, And so that will be the sum of the entries in this first row of the table. So it'd be true positives divided by true positives. I'm going to abbreviate positive as POS, and then plus false positives, again abbreviating positive using POS. So that's called precision, and as you can tell, high precision would be good. That means that of all the patients that we went to and we said, we're very sorry, we think you have cancer. High precision means that of that group of patients, most of them we had actually made accurate predictions on, and they do have cancer. The second number we're going to compute is called recall. And what recall says is, of all the patients in, let's say in the test set, or in the cross-validation set, but of all the patients in the data set that actually have cancer, what fraction of them did we correctly detect as having cancer? So if all the patients have cancer, how many of them did we actually go to them and correctly tell them that we think they need treatment? So writing this down, recall is defined as the number of positives, the number of true positives, meaning true positive, meaning the number of people that have cancer and that we correctly predicted have cancer, and we take that and divide that by the number of actual positives. So this is number of actual positives of all the people that do have cancer. What fraction did we correctly flag and send for treatment? So to rewrite this in a different form, the denominator would be number of actual positives is the sum of the entries in this first column over here. And so writing this out differently, this is therefore the number of true positives divided by the number of true positives plus the number of false negatives. And so once again, having a high recall would be a good thing. So by computing precision and recall, this will usually give us a better sense of how well our classifier is doing. And in particular, if we have a learning algorithm that predicts y equals 0 all the time, if it predicts no one has cancer, then this classifier will have a recall equal to 0 because there won't be any true positives, and so that's a quick way for us to recognize that a classifier that predicts y equals 0 all the time just isn't a very good classifier. And more generally, even for settings where we have very skewed classes, is not possible for an algorithm to sort of quote cheat and somehow get a very high precision and a very high recall by doing some simple thing like predicting y equals 0 all the time or predicting y equals 1 all the time. And so we're much more sure that a classifier with high precision and high recall actually is a good classifier, and this gives us a more useful evaluation metric. That's a more direct way to actually understand whether our algorithm may be doing well. So one final note in the definition of precision and recall. The way we define precision and recall, usually we use the convention that y is equal to 1 in the presence of the more rare class. So if we're trying to detect some rare condition, such as cancer, hopefully that's a rare condition, precision and recall are defined setting y equals 1 rather than y equals 0 to be sort of the presence of that rare class that we're trying to detect. And by using precision and recall, we find what happens is that even if we have very skewed classes, it's not possible for an algorithm to, quote, cheat and predict y equals 1 all the time or predict y equals 0 all the time and get high precision and recall. And in particular, if a classifier is getting high precision and high recall, then we're actually confident that the algorithm has to be doing well even if we have very skewed classes. So for the problem of skewed classes, precision and recall gives us more direct insight into how the learning algorithm is doing, and is often a much better way to evaluate our learning algorithms than looking at classification error or classification accuracy when the classes are very skewed. In the last video, we talked about precision and recall as an evaluation metric for classification problems with skewed classes. For many applications, we'll want to somehow control the trade-off between precision and recall. Let me tell you how to do that and also show you some even more effective ways to use precision and recall as an evaluation metric for learning algorithms. As a reminder, here are the definitions of precision and recall from the previous video. Let's continue our cancer classification example where y equals 1 if a patient has cancer and y equals 0 otherwise. And let's say we've trained a logistic regression classifier which outputs probabilities between 0 and 1. So as usual, we're going to predict 1, y equals 1, if h of x is greater than or equal to 0.5, and predict 0 if the hypothesis outputs a value less than 0.5. And this classifier may give us some value for precision and some value for recall. But now, suppose we want to predict that a patient has cancer only if we're very confident that they really do. Because, if you go to a patient and you tell them that they have cancer, it's going to give them a huge shock, give them seriously bad news, and they may end up going through a pretty painful treatment process and so on. And so maybe we want to tell someone that we think they have cancer only if they're very confident. One way to do this would be to modify the algorithm so that instead of setting this threshold at 0.5, we might instead say that we'll predict that y is equal to 1 only if h of x is greater than or equal to 0.7. So this is like saying we'll tell someone they have cancer only if we think there's a greater than or equal to 70% chance that they have cancer. And if you do this, then you're predicting someone has cancer only when you're more confident. And so you end up with a classifier that has higher precision, because all the patients that you're going to and saying, we think you have cancer, all of those patients are now ones that you're pretty confident actually have cancer. And so a higher fraction of the patients that you predict have cancer will actually turn out to have cancer, because we're making those predictions only if we're pretty confident. But in contrast, this classifier will have lower recall, because now we're going to make predictions, we're going to predict y equals 1 on a smaller number of patients. And we could even take this further. Instead of setting the threshold at 0.7, we could set this at 0.9, and we'll predict y equals 1 only if we're more than 90% certain that the patient has cancer. And so, a large fraction of those patients will turn out to have cancer. And so this will be a high precision classifier, but we'll have lower recall because we won't correctly detect that those patients have cancer. Now consider a different example. Suppose we want to avoid missing too many actual cases of cancer, so we want to avoid false negatives. In particular, if a patient actually has cancer, but we fail to tell them that they have cancer, then that could be really bad, because if we tell a patient that they don't have cancer, then they're not going to go for treatment. And if it turns out that they have cancer, but we fail to tell them they have cancer, well, they may not get treated at all, and so that would be a really bad outcome. They would just die because we told them they don't have cancer, they failed to get treated, but it turns out they actually have cancer. So suppose that when in doubt, we want to predict that y equals 1. So if when in doubt, we want to predict that they have cancer so that at least they look further into it and they at least can get treated in case they do turn out to have cancer. In this case, rather than setting higher probability threshold, we might instead take this value and instead set it to a lower value, so maybe 0.3, like so. Right? And by doing so, we're saying that, if we think there's more than a 30% chance that they have cancer, we better be more conservative and tell them that they may have cancer so that they can seek treatment if necessary. And in this case, what we would have is going to be a higher recall classifier, because we're going to be correctly flagging a higher fraction of all of the patients that actually do have cancer, but we're going to end up with lower precision, because a higher fraction of the patients that we said have cancer, a higher fraction of them will turn out not to have cancer after all. And by the way, just as an aside, when I talk about this to other students, I've been told before, it's pretty amazing. Some of my students say is how I can tell the stories both ways. Why we might want to, have higher precision or higher recall, and the story actually seems to work both ways. But I hope the details of the algorithm is true, and the more general principle is depending on whether you want high precision, lower recall, or high recall, lower precision, you can end up predicting y equals 1 when h of x is greater than some threshold. And so in general, for most classifiers, there's going to be a trade-off between precision and recall. And as you vary the value of this threshold, this value of this threshold I've been drawing here, you can actually plot out some curve that trades off precision and recall, where a value up here, this would correspond to a very high value of the threshold, maybe threshold equals 0.99. So that's saying predict y equals 1 only if we're more than 99% confident, or at least 99% probability this one. So that'll be a high precision, relatively low recall, whereas the point down here will correspond to a value of the threshold that's much lower, maybe equal 0.01, meaning when in doubt at all, predict y equals 1. And if you do that, you end up with a much lower precision, higher recall classifier. And as you vary the threshold, you can, if you want, you can actually trace out a curve for your classifier to see the range of different values you can get for precision and recall. And by the way, the precision recall curve can look like many different shapes. Sometimes it'll look like this, sometimes it'll look like that. There are many different possible shapes for the precision recall curve depending on the details of the classifier. So this raises another interesting question, which is there a way to choose this threshold automatically? Or more generally, if we have a few different algorithms or a few different ideas for algorithms, how do we compare different precision recall numbers? Concretely, suppose we have 3 different learning algorithms. Actually, maybe these are 3 different learning algorithms. Maybe these are the same algorithm, but just with different values for the threshold. How do we decide which of these algorithms is best? One of the things we talked about earlier is the importance of a single real number evaluation metric. And that is the idea of having a number that just tells you how well is your classifier doing. But by switching to the precision recall metric, we've actually lost that. We now have 2 real numbers. And so we often may end up faced with situations like if we're trying to compare algorithm 1 and algorithm 2, we end up asking ourselves, is the precision of 0.5 and a recall of 0.4, well, is that better or worse than the precision of 0.7 and a recall of 0.1? And if every time you try out a new algorithm, you end up having to sit around and think, well, maybe 0.5, 0.4 is better than 0.7, 0.1, or maybe not, I don't know. If you end up having to sit around and think and make these decisions, that really slows down your decision-making process for what things or what changes are useful to incorporate into your algorithm. Whereas in contrast, if we had a single real number evaluation metric, like a number that just tells us is algorithm 1 or is algorithm 2 better, then that helps us to much more quickly decide which algorithm to go with, and helps us as well to much more quickly evaluate different changes that we may be contemplating for an algorithm. So how can we get a single real number evaluation metric? One natural thing that you might try is to look at the average between precision and recall. So using P and R to denote precision and recall, one thing you could do is just compute the average and look at what classifier has the highest average value. But this turns out not to be such a good solution because, similar to the example we had earlier, it turns out that if we have a classifier that predicts y equals 1 all the time, then if you do that, you can get a very high recall, but you end up with a very low value of precision. Conversely, if you have a classifier that predicts y equals 0 almost all the time, that is, if it predicts y equals 1 very sparingly, this corresponds to setting a very high threshold using the notation of the previous slide, then you can actually end up with a very high precision but a very low recall. So the two extremes of either a very high threshold or a very low threshold, neither of that would give a particularly good classifier. And the way we recognize that is by seeing if we end up with a very low precision or a very low recall. And if you just take the average of P plus R over 2, well, in this example, the average is actually highest for algorithm 3, even though you can get that sort of performance by predicting y equals 1 all the time. And that's just not a very good classifier, right? If you predict y equals 1 all the time, it's just not a useful classifier if all it does is print out y equals 1. And so algorithm 1 or algorithm 2 would be more useful than algorithm 3. But in this example, algorithm 3 has a higher average value of precision recall than algorithm 1 and 2. So we usually think of this average of precision recall as not a particularly good way to evaluate our learning algorithm. In contrast, there's a different way for combining precision and recall. It's called the F-score, and it uses that formula. And so in this example, here are the F-scores. And so we would tell from these F-scores that it looks like algorithm 1 has the highest F-score, algorithm 2 has the second highest, and algorithm 3 has the lowest. And so, if we go by the F-score, we would pick probably algorithm 1 over the others. The F-score, which is also called the F1 score, is usually written F1 score like I have here, but often people will just say F-scores. Either term is used. Is a little bit like taking the average of precision and recall, but it gives the lower value of precision and recall, whichever it is, it gives it a higher weight. And so you see in the numerator here that the F-score takes a product of precision and recall. And so if either precision is 0 or recall is equal to 0, the F-score will be equal to 0. So in that sense, it kind of combines precision and recall, but for the F-score to be large, both precision and recall have to be pretty large. I should say that there are many different possible formulas for combining precision and recall. This F-score formula is really maybe just one out of a much larger number of possibilities, but historically or traditionally, this is what people in machine learning seem to use. And the term F-score, it doesn't really mean anything, so don't worry about why it's called F-score or F1 score. But this usually gives you the effect that you want, because if either precision is 0 or recall is 0, this gives you a very low F-score. And so to have a high F-score, you kind of need a precision recall to be 1. And concretely, if P equals 0 or R equals 0, then this gives you that the F-score equals 0. Whereas a perfect F-score, so if precision equals 1, and recall equals 1, that would give you an F-score that's equal to 1 times 1 over 2 times 2. So the F-score would be equal to 1 if you have perfect precision and perfect recall. And intermediate values between 0 and 1, this usually gives a reasonable rank ordering of different classifiers. So in this video, we talked about the notion of trading off between precision and recall, and how we can vary the threshold that we use to decide whether to predict y equals 1 or y equals 0. So there's a threshold that says, do we need to be at least like 70% confident or 90% confident or whatever before we predict y equals 1. And by varying that threshold, you can control a trade-off between precision and recall. We also talked about the F-score, which takes precision and recall and again gives you a single row number evaluation metric. And of course, if your goal is to automatically set that threshold to decide when to predict y equals 1 and y equals 0, one pretty reasonable way to do that would also be to try a range of different values of thresholds. So try a range of values of threshold and evaluate these different thresholds on, say, your cross-validation set, and then to pick whatever value of threshold gives you the highest F-score on your cross-validation set. And that'd be a pretty reasonable way to automatically choose the threshold for your classifier as well. In the previous video, we talked about evaluation metrics. In this video, I'd like to switch tracks a bit and touch on another important aspect of machine learning system design, which will often come up, which is the issue of how much data to train on. Now, in some earlier videos, I had cautioned against blindly going out and just spending lots of time collecting lots of data, because it's only sometimes that would actually help. But it turns out that under certain conditions, and I'll say in this video what those conditions are, getting a lot of data and training on a certain type of learning algorithm can be a very effective way to get a learning algorithm to give very good performance. And this arises often enough that if those conditions hold true for your problem, and if you're able to get a lot of data, this could be a very good way to get a very high performance learning algorithm. So in this video, let's talk more about that. Let me start with a story. Many years ago, two researchers that I know, Michelle Banco and Eric Bro, ran the following fascinating study. They were interested in studying the effect of using different learning algorithms versus trying them out on different training set sizes. They were considering the problem of classifying between confusable words. So for example, in the sentence, for breakfast I ate, should it be T-O, T-W-O, or T-O-O? Well, for this example, for breakfast I ate T-W-O 2 eggs. So this is one example of a set of confusable words, and that's a different set. And so they took machine learning problems like these, sort of supervised learning problems, to try to categorize what is the appropriate word to go into a certain position in an English sentence. They took a few different learning algorithms which were, sort of considered state-of-the-art back in the day when they ran this study in 2001. So they took a variant, roughly a variant on logistic regression called the perceptron. They also took some of their algorithms that were state-of-the-art back then but are somewhat less used now. So the winnow algorithm, also very similar to logistic regression but different in some ways, much used, somewhat less, used not too much right now. Took what's called a memory-based learning algorithm, again used somewhat less now. I'll talk a little bit about that later. And they used the naive-based algorithm, which is something that I'll actually talk about in this course. The exact algorithms of these details aren't important. Think of this as just picking 4 different classification algorithms, and really the exact algorithms aren't important. But what they did was they varied the training set size and tried out these learning algorithms on a range of training set sizes, and that's the result they got. And the trends are very clear, right? First, most of these algorithms give remarkably similar performance. And second, as the training set size increases, on the horizontal axis is the training set size in millions. As you go from 100,000 up to 1,000 million, that is a billion training examples, the performance of the algorithms all pretty much monotonically increase. And in fact, if you pick any algorithm, maybe pick a quote inferior algorithm, but if you give that quote inferior algorithm more data, then from these examples, it looks like it will most likely beat even a quote superior algorithm. So since this original study, which is very influential, there's been a range of many different studies showing similar results that show that many different learning algorithms can sometimes, depending on the details, can give pretty similar ranges of performance. But what can really drive performance is if you can give the algorithm a ton of training data. And this is results like these has led to a saying in machine learning that often in machine learning is not who has the best algorithm that wins, is who has the most data. So when is this true and when is this not true? Because if we have a learning algorithm for which this is true, then getting a lot of data is often maybe the best way to ensure that we have an algorithm with very high performance, rather than debating, worrying about exactly which of these algorithms to use. Let's try to lay out a set of assumptions under which having a massive training set we think will be able to help. Let's assume that in a machine learning problem, the features X have sufficient information with which we can use to predict Y accurately. For example, if we take the confusable words problem that we had on the previous slide, let's say that the features X capture what are the surrounding words around the blank that we're trying to fill in. So the features capture that we have a sentence for breakfast, I ate blank eggs. Then that's pretty much enough information to tell me that the word I want in the middle is TWO, and that is not the word TO, and is not the word TOO. So the features capture, what are these surrounding words, then that gives me enough information to pretty unambiguously decide what is the label Y, or in other words, what is the word that I should be using to fill in that blank out of this set of 3 confusable words. So that's an example of where the features X have sufficient information to predict Y. For a counterexample, consider the problem of predicting the price of a house from only the size of the house and from no other features. So If you imagine I tell you that a house is, 500 square feet, but I don't give you any other features. I don't tell you if the house is in an expensive part of the city, or if I don't tell you if the house, the number of rooms in the house, or how nicely furnished the house is, or whether the house is new or old. If I don't tell you anything other than that this is a 500 square foot house, well, there are so many other factors that will affect the price of a house other than just the size of the house, that if all you know is the size, it's actually very difficult to predict the price accurately. So that would be a counterexample to this assumption that the features have sufficient information to predict the price to the desired level of accuracy. The way I think about testing this assumption, one way I often think about it is I'll often ask myself, given the input features X, so given the features, given the same information available to a learning algorithm, if we were to go to a human expert in this domain, can a human expert accurately, or can a human expert confidently predict the value of Y? For this first example, if we go to, an expert human English speaker, like you go to someone that speaks English well, right? Then a human expert in English, just really most people like you and me, would probably be able to predict what words should go in here. So a good English speaker can predict this well, and so this gives me confidence that X allows us to predict Y accurately. But in contrast, if we go to an expert in human prices, like maybe an expert realtor, right, someone who sells houses for a living, if I just tell them the size of the house and I tell them what the price is, well, even an expert in pricing or selling houses wouldn't be able to tell me. And so that's a sign that for the housing price example, knowing only the size doesn't give me enough information to predict the price of the house. So let's say this assumption holds. Let's see then when having a lot of data could help. Suppose the features have enough information to predict the value of Y, and let's suppose we use a learning algorithm with a large number of parameters. So maybe logistic regression or linear regression with a large number of features, or one thing that I sometimes do, one thing that I often do actually, is use a neural network with many hidden units. That would be another learning algorithm with a lot of parameters. So these are all powerful learning algorithms with a lot of parameters that can fit very complex functions. So I'm going to call these, we're going to think of these as low bias algorithms because they can fit very complex functions. And because we have a very powerful learning algorithm that can fit very complex functions, chances are if we run these algorithms on a data set, it will be able to fit the training set well, and so hopefully the training error will be small. Now let's say we use a massive training set. In that case, if we have a huge training set, then hopefully, even though we have a lot of parameters, but if the training set is sort of even much larger than the number of parameters, then hopefully these algorithms will be unlikely to overfit, right? Because we have such a massive training set. And by unlikely to overfit, what that means is that the training error will hopefully be close to the test error. Finally, putting these two together, if the training set error is small and the test set error is close to the training error, what these two together imply is that hopefully the test set error will also be small. Another way to think about this is that in order to have high performance learning algorithm, we want it not to have high bias and not to have high variance. So the bias problem we're going to address by making sure we have a learning algorithm with many parameters, and so that gives us our low bias algorithm. And by using a very large training set, this ensures that we don't have a variance problem either. So hopefully our algorithm will have low variance. And so it's by putting these two together that we end up with a low bias and a low variance learning algorithm, and this allows us to do well on the test set. And fundamentally, it is the key ingredients of assuming that the features have enough information and we have a rich class of functions. That's what guarantees low bias. And then it's having a massive training set that's what guarantees low variance. So this gives us a set of conditions, or hopefully some understanding of what's the sort of problem where if you have a lot of data and you train a learning algorithm with a lot of parameters, that might be a good way to give a high performance learning algorithm. And really, I think the key tests that I often ask myself are, first, can a human expert look at the features X and confidently predict the value of Y? Because that's sort of a certification that Y can indeed be predicted accurately from the features X. And second, can we actually get a large training set and train a learning algorithm with a lot of parameters in that training set? And if you can do both, then that will often give you a very high performance learning algorithm.